Okay guys, in this video we are going to introduce the definition of entropy, and we'll talk about it from a couple of different perspectives, both a microscopic perspective and a macroscopic perspective. And then at the very end I'm going to show you a very important conceptual type of problem that you'll need to know about for the exam. That is, you need to be able to predict the sign of the entropy change for different chemical and physical processes. So we're going to start with a microscopic definition of entropy, which is a little abstract, but in the end it really only involves counting. Okay, so the idea here, entropy, it's a state function. It has the symbol S, and we'll talk about the units here in a minute. It is given by the logarithm of the number of microstates that are available to a system in a given macrostate. I'll start with the macrostate. A macrostate is just what we've been talking about previously during the review, where we talked about thermodynamic states. So the term macrostate refers to the thermodynamic state of your system. So if you had a gas, the macrostate of that ideal gas would be described by its pressure, its volume, number of moles, and temperature. So if you know those four quantities, then you have specified what macrostate you're talking about. The idea of a microstate involves the actual molecules of the gas. And so from one perspective, you could specify the microstate of a system by stating the position and velocity of every gas molecule in your sample. So let's suppose that you had a mole of gas molecules, so something like 10 to the 23 gas molecules. If you could define the position and velocity of all of those different gas molecules, that would be the microstate of the system. And the next concept here is that multiple microstates correspond to the same macrostate, and that's what a distribution is. So a distribution of microstates is a group of energetically equivalent microstates. And so think about a gas, you know its pressure, volume, number of moles, and temperature. The molecules are in constant motion. So you have one macrostate defined by those variables. All the while, the molecules are moving around, they're bouncing all over the place. Their microstate is changing all the time. And all of the different microstates that the system can explore correspond to the same macrostate. They form a distribution of equivalent microstates. The entropy of the macrostate is defined as the logarithm of the number of microstates corresponding to that macrostate. And the factor in front, K, is called the Boltzmann constant, and it has a value of 1.38 times 10 to the minus 23 joules per Kelvin. So the entropy, or the units of entropy, are joules per Kelvin. From the microscopic perspective, the entropy is the logarithm of the number of microstates available to the system. And so in principle, you would count those up. So how many different molecular configurations are possible for your sample of gas? You calculate that number. It's actually going to be enormous. And then you take the logarithm of that number and then multiply by the proportionality factor, the Boltzmann constant. So in principle, that's all that entropy is. You count up the number of different possible configurations of your system at the microscopic level and take the logarithm. To calculate the change in entropy, since entropy is a state function, it'll be the final entropy minus the initial entropy. And if you substitute in this definition, the microscopic definition of entropy, in for SF and SI, you can get an expression that looks like this, using the rules of logarithms. One of the observations of thermodynamics is that the most probable distribution, that is, the most probable macrostate, is the one that corresponds to the largest number of microstates and hence also has the largest entropy. So in nature, there's a tendency to maximize the number of microstates available to the system, and in doing so, you also maximize the entropy of the system. Let's put this concept into practice using some very simple examples. So instead of having a gas with 10 to the 23 molecules, we're going to consider a sample of gas that has only 4 molecules. And those are represented by these colored dots here, the red, the green, the blue, and the yellow. Those represent 4 molecules. And they are enclosed in a volume. So the 2 boxes here represent the total volume. And in this configuration A here, all of the gas molecules are on one side of their container. Okay, and so there is only one way to rearrange 4 molecules in 2 boxes where all of the molecules are only in one side of the container. Okay, so there is one microstate available to the macrostate A. A second macrostate would involve having 3 molecules on one side and 1 molecule on the other side. And there are different ways to rearrange the molecules across these 2 different boxes. So you could have the blue, the yellow, and the green on one side, and the red is the odd one out. Or you could make the green one the odd one out, or the blue one, or the yellow one. So these 4 scenarios here correspond to 4 different microstates corresponding to the macrostate with 3 molecules on one side and 1 molecule on the other. A third macrostate would involve having 2 molecules on each side of the container. And what's enumerated here are the different ways in which you could do that with these four circles. So you could have the red and the green on the left and the blue and the yellow on the right, or you could do the red and the blue on the left and the green and the yellow on the right, and so on. And if you look, there are 2 additional microstates corresponding to this distribution. Okay, so there's more ways you can rearrange the molecules when 2 are on the left and 2 are on the right. Case D here is the opposite of case B, where we'll only have 1 molecule on the left and 3 on the right, and you have the same number of microstates in macrostate D as you do in macrostate B. And then E is sort of the opposite of macrostate A, where instead of all of the molecules on the left, they're all on the right, and there's only one way to rearrange the molecules in that case. So of these different macrostates, these different distributions, the one with the largest number of microstates is macrostate C, where we have the greatest dispersion of matter. So this macrostate has the largest number of microstates. It's going to have the largest entropy. It's going to be the most probable state. And indeed, that's what we see in nature. For example, I'm going to skip back to the last section and make a connection to this figure here. Right? We talked about how in the last video that there is a tendency for material systems to evolve into a state where you have the greatest distribution of matter throughout the system. And so when you open the valve here in this vessel, the gas will spontaneously on its own fill both chambers. Okay, and there's nothing like you would never ever expect for the gas to go from this situation here where you have the greatest dispersion of matter to one where all of the matter is on one side of the vessel. It just won't happen on its own. It's essentially the same thing that's going on here in this example. You've got here all of the gas molecules are on one side. In this macrostate, you've got an equal amount of gas on either side. The macrostate where you have the greatest dispersion of matter is the most probable state. Here we have another example. This one involves the dispersion of energy. We have an object that consists of 2 halves, and we'll suppose that each half has two molecules. So there's molecules A, B, C, and D in this system. And the stars in these figures represent units of thermal energy. So for the first macrostate, what we're going to do is we're going to place both units of energy on the left, and we're going to count the different ways in which we can do that. So you can have both units of thermal energy on molecule A, or you can have both units of thermal energy on molecule B, or you can distribute the units equally across the two molecules that you have on the left-hand side. So there are 3 microstates corresponding to having the 2 units of thermal energy on the left. In part C, it's basically the same thing, except for we have the 2 units of thermal energy on the right-hand side. And so you can either put them both on C, you can put them both on D, or you can split them up among C and D. In macrostate B, what we're doing is we're distributing the energy across the system. We will have 1 unit of thermal energy on the left and 1 unit of thermal energy on the right. And what we'll do is we'll enumerate the number of ways in which you can do that. So you can have the unit of energy on A and 1 on C. You can put 1 on A and 1 on D, or B and C, or B and D. And so for part B, we see that as we distribute the energy across both sides of the system, there are more microstates available. So this macrostate has more microstates, it has a larger entropy, and it's the more probable of the macrostates. And this example is analogous to this picture here, where you take a hot object that has a higher thermal energy and bring it into contact with a cold object that has a lower thermal energy. And the spontaneous change that occurs is that heat flows from the hot object to the cold object until both sides of the combined object are in thermal equilibrium. And once you've distributed that thermal energy evenly across both sides, you never ever observe it to spontaneously go back to having a hot side and a cold side. It just doesn't happen on its own without doing work. So distributing matter increases the entropy in the system. Dispersing energy increases the entropy of the system. Well, in this example, this is mostly for the sake of your sapling homework. You'll find some little problems like this on the sapling. Let's just review what they want you to do in these types of calculations. So they want us to calculate the entropy change for a process that takes us from distribution A to distribution C in that particle in a box example. So let's just take a quick look here. They want us to go from this distribution, this macrostate, to this macrostate and calculate the entropy change. And recall what we need to know the number of microstates for each distribution. So distribution A has 1 microstate, distribution C has 1, 2, 3, 4, 5, 6 microstates available to it. So W for state A is 1, there's 1 microstate. W for state C is 6. We can calculate the entropy change as the difference between the 2 entropies using the microscopic definition of entropy, Boltzmann's constant times the natural log of the number of microstates for macrostate C minus the same thing for state A. We can combine these two into one term using the rules of logarithms, and you just plug in 6 divided by 1, and so you would calculate k times the natural log of 6. I didn't complete the calculation. To complete it, you would just plug in that value of k, 1.38 times 10 to the minus 23 joules per Kelvin, and that would give you your delta S value. For part B here, they want us to use the hot-cold objects, and they want us to calculate the entropy change for going from this state A here to state C here. That is, take all of the excess thermal energy on the left and move it all to the right. And so we need the number of microstates in each of these macrostates. There's 3 in macrostate A, and there's also 3 in macrostate C. And so when you go to calculate the change in the entropy, you get a ratio of 3 divided by 3, which is just 1, and the natural log of 1 is 0. So when you go from this state to that state, the two states are essentially equivalent to one another, and so there's no change in the entropy. Well, we'll move on next to the macroscopic definition of entropy. Unfortunately, it's just about as abstract as the microscopic definition, but we will get an application out of it. So in macroscopic terms, the entropy of a system is a measure of the system's thermal energy that is unavailable to do useful work. Okay, so that's a bit strange, but it helps to understand the context in which entropy was originally introduced historically. At the time, scientists were interested in studying engines, heat engines, for example. The goal was to make engines as efficient as possible, and so what they wanted to understand was how much heat can be converted into work. And what came from that work is that there's always some amount of thermal energy that is lost via heat that can't be used to do useful work. And so that's where this funny definition comes from. Part of that work, or I should say part of the work involved in developing entropy involves the idea of a reversible process, which is a hypothetical type of process that occurs where the system and the surroundings are always in thermal equilibrium. So for this hypothetical process, it turns out that this is the most efficient way in order to extract work from a system. And so the entropy change for calculating, the way that you go about calculating the entropy change for a process involves considering a reversible process. And if the process is carried out at constant temperature, the entropy change for the system is equal to the reversible heat divided by the temperature at which the process is carried out. And what you find at the end of the day is that you cannot convert thermal energy to work with 100% efficiency. You always lose some energy as heat. Here, this is a much more important slide for us to consider. So this is the most important slide in the presentation for this video. Here we have essentially a statement of the second law of thermodynamics, which tells us that a process will be spontaneous if the entropy of the system and surroundings increases. Okay, so what this does is it allows us to distinguish between spontaneous processes and non-spontaneous processes. And so the entropy of the system plus the entropy of the surroundings, the sum of those two quantities will increase for any spontaneous process. For a non-spontaneous process, that total entropy change would be negative. So S is a thermodynamic state function. It's extensive, so that means that it increases with the size of the system. It has units of joules per Kelvin. And here I've given you some typical situations where the entropy of the system, at least, will increase. When you mix things together randomly, so if you take two liquids and mix them together to form a solution, that usually increases the entropy of the system. Whenever you heat your system up, so if the system's temperature increases, the entropy change will be positive. And then for any chemical reaction where gases are produced, that is also going to increase the entropy of the system. And right down here is probably the most important relationship in the chapter, for working through the exam. It tells us that the molar entropy, so that's what the dash over the entropy symbol means. The entropy per mole of solid is less than the entropy per mole of liquid, and both of those are much, much less than the entropy per mole of gas. And the reason this is true can be understood in terms of the microstates available to the system, or rather the number of microstates available to the system. In a solid, the molecules of the solid are held rigidly in place. They can't move around very much, and so the number of available microstates to the molecules of the solid is small. For the liquid, the molecules can move around, but they can't get too far away from one another. Okay, so there's a bit more mobility, and so the number of microstates available to the system is greater than that of the solid, but they're still held together. However, for a gas, the gas molecules are moving around randomly, essentially, and there are many, many more microstates available to a gas than there are to a liquid or to a solid. And we are going to use this relationship to help us eyeball what the sign of delta S will be for a given chemical reaction. First, I think I have some graphical representations. So this is a graphical representation of the relationship that I just showed you. The entropy of a solid is less than the entropy of a liquid. So as you go from a solid to a liquid, if you melt the solid, the entropy is going to increase. And then if you go from a liquid to a gas, the entropy is going to increase even more. And that's actually represented here in this figure. We're plotting entropy versus temperature. As you heat up a solid from low temperature, you see that the entropy increases more or less linearly in this graph. And then once you get to the melting point, you get a sudden jump in the entropy as you form the liquid. And then as you continue to heat the liquid, you see that the entropy increases again. When you get to the boiling point, you have a very large jump in the entropy when you form the gas. And then as you heat the gas up, the entropy of the gas increases as you increase its temperature. So in this figure, we're illustrating both this rule here and that one and this one as well. Okay, so the temperature increase and then the relationship between entropy and the various phases of matter. So this is something that you want to practice. And if Sapling isn't giving you enough practice with this, then I strongly urge you to use the end of chapter questions to test yourself. And so here we're just given different processes, and we're asked to determine what is the sign of the entropy change. Is it going to be positive? Does entropy increase? Or will it be negative? Does entropy decrease? In part A, what we're doing is we're heating up water at room temperature, and we're heating it up to 50 degrees Celsius, which is above room temperature. So you're increasing the temperature of the liquid. That is going to increase the entropy of the liquid. And so this is going to be a positive delta S for part A. For part B, we have ions coming together to form a precipitate. Okay, so you have ions in aqueous solution, and then you have the solid on the right-hand side. And so if we go back to this relationship here, that solids have a lower entropy than liquids, which have a lower entropy than gases, we can use that to address part B. In the aqueous phase, the ions can move around, but in the solid phase, the ions are held more or less in place in the crystal. And so we would say that the solid has a lower entropy than the ions that are moving around in the aqueous phase. And so this would correspond to a negative delta S. For part B, we see that we have a heterogeneous reaction. We've got liquids and gases. Really, all you need to do is count the number of moles of gas on each side of the reaction. And the side that has more moles of gas will have the larger entropy. So on the left-hand side, we've got 7.5 moles of oxygen gas, and on the right-hand side, we have 6 moles of carbon dioxide gas. So the number of moles of gas decreases in this reaction, and so delta S will be negative. For part D, we are melting a solid. We're melting solid ammonia to liquid ammonia. Liquids have a larger entropy than solids, therefore delta S will increase for part D. Part E is very much like part B, only it's a dissolution reaction. So we have the sodium nitrate solid that's dissociating to form the ions. The ions are more mobile in the aqueous phase than they are in the solid phase. And so for part E, the entropy change increases as you dissociate the solid. For part F, this is a sublimation reaction. You have solid CO2 sublimating to carbon dioxide gas. The gas has a much, much larger entropy than the solid, and so delta S is positive for part F. In part G, we have a decomposition reaction. Calcium carbonate is decomposing into calcium oxide and carbon dioxide gas. We simply need to look at the number of moles of gas on each side. There are no moles of gas on the reactant side. There's 1 mole of gas on the product side. The number of moles of gas increases. Therefore, the entropy change for this reaction is going to be positive. This is the type of thinking that you're going to need to execute on the next exam. You'll be faced with questions that will give you, for example, 5 reactions, and the question will be, for which of the following reactions does the entropy increase? Or for which of the following reactions does the entropy decrease? Well, I think that's the last slide I have in this section, so I'm going to end the video right here.